talking about color unified dynamical axion. This is work I did at the IFT under the Elusives grants, and I did this work in collaboration with Mary Kay Gaillard at Berkeley and Bailyn Gamela at the IFT, plus two PhD students at the IFT, Rosita Del Rey and Pablo Quiles. QCD has a strong CP problem. QCD predicts non-preservative interaction that has a coupling that looks like this and introduces CP violation into standard model. And so if this interaction was here, there would be experimental signals. One of the most famous ones is the electric dipole moment of the neutron, which can show up through like a low energy effective Feynman diagram that looks like this. And the actual CP comes in through this physical CP violation, which is this bare beta terminal Lagrangian plus complex spaces of the Apollo couplings. And experiment has put very strict bounds on this physical CP violating parameter, theta bar, to be less than 10 to the minus 10. So as theorists, our question is to either justify this very small number without fine-tuning, or explain maybe this interaction term isn't there, but if it's not there, we need to explain why. One way to solve the strong CP problem is to introduce a massless quark into your theory. So if you just have a normal quark in your theory, there's some mass term, QRQ, and then this non-perturbative interaction with theta. And if you do a chiral rotation on your quark fields, you get a phase that looks like this. And then this also corresponds to a vacuum-to-vacuum transition in the QCD vacuum, which introduces, if this phase is alpha, a shift in theta that goes like alpha. So if you have a massless quark, if MQ is 0, then this chiral rotation, its only physical effect on the Lagrangian is just redefining your fields. And so this means that your Lagrangian is invariant over the shift symmetry, and you can shift theta to be 0. So then this coupling is non-physical, and you would expect no CP violation in your Lagrangian. So the simplest version of the massless quark solution is that the lightest standard model quark would be massless, the up quark. Then like the bare mass of the up quark could be 0. Although lattice groups have been doing calculations to try and calculate the bare mass of the up quark. And it seems like MU equals 0 is highly disfavored by lattice data. Whether or not it's ruled out, like what the significance of this calculation is, seems a bit unclear right now in the literature, but it's definitely not favored that the up quark is 0. Although there's no problem with the massless quark being an exotic quark, if an exotic quark does solve the strong CP problem and it's massless, it has to be hidden by some mechanism. To explain why we haven't seen it. Probably the most famous solution is the axion. So you introduce a new U1 Pechiquin solution, or symmetry, to your Lagrangian. When the U1 breaks, there's a resulting pseudo-Goldstone boson, which is the axion. The pseudo-Goldstone boson has interactions in your Lagrangian, has a potential. When you minimize the axion, you can shift this parameter to 0 and get no CP violation or very, very small CP violation in your Lagrangian. So invisible axion models that are like sort of the most typical simple implementation of this say that axions sort of live on a line in parameter space. So the mass of the axion and the decay constant of the axion are related that go like some constant like m pi f pi. So what this looks like is,
so if you ever to give this talk at Stanford or MIT or some other places, you should put the real original references.
These aren't the real original ones?
No, absolutely not.
But they all have so many citations on Inspire.
I know, but it's like Piché and Quinn and...
Oh, that's the PQWW axion.
Yeah.
But I'm talking about the KSV side.
I know, but yeah, since you're sort of introducing, I'm just saying, I don't care, but just since you're talking about the Axion solution, you should really...
Yeah, I don't put it... Oh, I don't have it here, you're right. Yeah, I should put the PQ tapers, you're right. I agree, yeah. Sorry, I guess I got too excited with the... Yeah, my DSVZ, KSVZ citations take up too much space. Yeah, that's a good point. All right. Yeah, I should put Pechiquin on here. I even have PQ on this slide. Thanks. I'm going to Santa Cruz, so maybe I'm more nervous about Michael dying. So yeah. All right, so this parameter space. So we have, here's like from the PDG, just a summary of axion searches. So on the x-axis, we have the axion mass in EV. And on the y-axis, we have the coupling of the axion to photons, which is proportional to this like FA parameter in the theory. As you can see, this line here in yellow is sort of the preferred KSVZ DFSZ line for invisible axions. So axions are sort of stuck in this line based on the typical invisible axion theories. And if we look to higher mass axions, so this is basically the same plot except before MA went up to about an EeV. Now I found one that extends it to higher mass for the axion, and I just sketched the same invisible axion line on this graph. In higher mass, you can see colliders are sort of sensitive maybe to this region of axion parameter space, which isn't along this line. Or if it is, they've really ruled out the part that is along this line. So there's some theoretical motivation to sort of think about possible solutions with axions that are like collider observable, right, who live outside this MA-FA parameter space, which was the original motivation for this project, although we end up with sort of different phenomenology than we expected.
So, I mean, it's not going to solve the strong CP problem once it's about so about 10 to the 9.
I disagree, but maybe we can talk about it. We get pretty massive axions in our model.
If it's heavier than a GeV, then okay. Well, that's
Yeah, you're saying it gets integrated out, right?
I would think so.
So, all right, we'll talk about it. All right, so some models that are sort of along the same line of my model to give you an introduction to what I'm going to be doing with exotic massless quarks. So a long time ago in the 1980s, Choi and Kim wrote this paper, ACUT, where they add a new massless quark to their theory, this psi, and it's charged under QCD, so it has the ability to rotate away this theta CP. But they want to hide it somehow, so they introduced this axi-color group, SUN tilde, and they set it up so that SUN tilde confines at a much higher scale than QCD, right? And so when SUN tilde confines, even a massless quark charged under this color group will form downstates near the confinement scale, right? And so in this sense, they can sort of remove this massless quark from the theory or hide it. The problem is, if you introduce a new SUN tilde, it has its own CP violating angle theta tilde, and this quark connects the two sectors of the theory, right? So this CP violation from theta tilde can contaminate QCD CP violation. We would see it in the neutron, in the electrostatical moment of the neutron. So their solution to this problem is to absorb theta tilde by adding another massless quark to the theory. So they extend their theory to have another massless quark chi, which is only charged under SUN tilde. Right? And so now both massless quarks have absorbed both theta parameters. And so when SUN tilde confines, from SUN tilde's point of view, there are four flavors, red, green, blue, chi. And you get this chiral symmetry breaking SU4 left across SU4 right to SU4b. And this breaking scheme looks like 15 pseudo-Goldstone bosons. So we get adjoint exotic pions, fundamental, and a singlet exotic pion. And in their model, this is the eta, and it becomes the dynamical axion. And so what they did is they set their decay constant to be, or their decay constant is the confinement scale of SUN tilde, which they set to be a very high confinement scale. And they end up with exactly the same invisible parameter axion space, a low mass axion and a high scale for the axion. And this is sort of a UV completion for the typical invisible axion model. Hook put another solution to the strong CP problem with massless quarks. So Hook more recently did the same thing. So he throws in a new massless quark charged under two gauge groups. And the two gauge groups are related by a Z2 symmetry. And so in this sense, the two theta angles are related to one another. So if you absorb one, you absorb the other because they're related by the symmetry. So you don't need to introduce another massless quark. This Z2 copied the entire standard model. And so what he did is he broke the Z2 and set up one Higgs web to be much larger than the standard model Higgs. So this accomplished two things at the same time, right? First, it explained why we don't see all this hidden mirror world standard model content, right? And the second thing is that if this Higgs web is much larger, then the mass of the mirror world quarks are much larger than the standard model quarks. So if at some high scale these guys have the same gauge coupling, if there's more matter charged under here than under here, this confines much faster, so it confines at a higher scale. And so this allowed the mirror QCD to confined at a higher scale than QCD, and then you get the bound states of the psi sitting around the QCD prime confinement scale. Yeah.
This is related to the twin Higgs model, right? With the Z2 signature that you have another.
I mean, there is a twin Higgs, yeah.
Essentially.
Yeah, but he wrote this model with the massless quark specifically to solve the Schwarzschild problem. But yeah, it's the same deal. Twin models, and then the tuning here is just that one Higgs web is set up to be much, much larger than the other. All right, so what we did is sort of along the same lines. So we introduced a new massless fermion to absorb the QCD theta angle. And we want to introduce a new gauge group so that this massless fermion can form bound states around the confinement scale of this new gauge group. And we're going to relate the two groups, but instead of relating them through a Z2 symmetry, we relate them through unification. So this will be an alternative to ACUT. The fact that we use unification instead of two massless quarks will give different phenomenology and more freedom in the MA-FA parameter space. All right, so let's talk about how we do this. So we start with SU6, which is going to be our color unified theory. So you're going to see the word cut instead of gut a lot because it's not grand unification, it's just color unification. So in our high energy theory, we have SU6, and then we also have SU2 left and hypercharged. So these guys aren't living inside the color unified group. This group is just color being unified. And then SU6 breaks to SU3 color, SU3 tilde, and U1. And we put our massless quark in the 20 representation of SU6. So upon breaking, we get these fields, which are charged this way under QCD and SU3 tilde. So we get something that is box, box, bar under both. And then we get another partner that's box, bar, box, which could form a conjugate. So these guys could come together and form gauge singlets. And then we also get these sterile neutrinos that are singlets under the whole standard model and very, very light or massless, depending on further games you want to play. All right, so the big problem we have right now with our theory is the standard model fermions, right? So we have the standard model fermion, or the standard model quarks are charged under QCD, right? And QCD lives inside this SU6, so we need to put them inside SU6 fields. So we put them just in the simple fundamental representation of SU6, so that under breaking we have them in the 3 of QCD and the 3 of QCD tilde. So we have this Q tilde, UU tilde, DD tilde for the quarks. And we want these SU6 partner fields to be decoupled, right? So we want the mass of Q tilde to be much larger than the mass of Q, the same with U tilde and D tilde. And we want these to be decoupled because obviously the mass of the partners are phenomenologically forbidden. And then we have the same problem Hook had, right? Like at some high scale, our two color groups are unified, so they have the same gauge coupling, right? So we want one to have a higher confinement scale than the other. It better have less matter content charge under it. So we really need to remove these guys at some high scale so that this guy can confine before this guy. And this is actually not so easy to do. So actually, I should have said earlier, I think I had the citation on this slide, but we're not the first people to do unification with strong CP problem. Gergetta did it with just a single axion and unification. Unification related to the two theta angles, and then the axion absorbed both. And in his paper, he sort of left it to an appendix for how to decouple these partner fields. But for us, we actually tried to do it in detail. And it's not trivial, or at least for us, it was not trivial for us to figure out how to do it. So especially this guy, he makes things really difficult, right? So under the current charge assignments we have, anything that gives like a typical Higgs mechanism would be charged as an SU2 left doublet, right? So we don't want to set up some Higgs VEV that's much, much higher than this VEV, because we don't want to affect electroweak symmetry breaking at some high scale. So we don't want to do this. And then actually we're still really forced to give these quarks masses above the confinement scale of SU3 tilde, even if we could appeal to some other mechanism to force SU3 tilde to confine first. These guys really have to be integrated out of the theory, because if they're still hanging around and they're massless, when SU3 tilde confines, if this is charged under SU2 left, we're going to break electroweak symmetry at the tilde confinement scale, right?
So what, couldn't you just, at the scale where you break SU6 into SU3 plus SU3, you could have, you know you're going to need to have, to arrange things so that you have a Higgs that you have a Higgs that I mean, the simplest thing is that the Higgs just couples equally to your Q and Q tilde fields.
It
right?
has to because it has to talk to the SU6 theory. So it has to
Right,
couple the
but
Q6
since but when
fields.
SU6 gets broken, right,
Mhm.
below that scale, that there's no longer a rule that they have to have the same.
But whatever fields you write down, they have to like apply to the above the unification
So,
scale,
you know
right?
what, I'm sorry, I shouldn't.
Yeah, so
think
it's not
out
quite
loud
the
during
Z2
some of that.
example, yeah,
You're
it's a
right,
little
not- I
more
don't see it.
constrained
I
than
thought
what.
I saw some simple way.
Yeah. So I don't think we can play the game hook play, right? Because we really don't have like two separate Higgs fields, we just have one Higgs. I mean, we could throw another one in, but then it talks to the standard model and the tildes, right? Because they're both living in these 6 splits, so. I mean, if you see a simpler way, like that would be awesome because our paper is very complicated because of this exact problem. This requires more model building. All right, so what do we have? What's our matter content above and below the cut breaking? So above cut, we have SU6, breaks into SU3 color, SU3 tilde, and our fields living in SU6. We have our 6 splits, our Q left, U right, D right, charged the typical way under SU2 left, and then we have our massless quark. Below the breaking, the massless guys are still in blue. And then we have the standard model guys charged under QCD living here. And then the tilde guys charged under tilde living here. And the goal is to provide a mechanism for these fields to be removed from the theory. So that's what we want. And the spoiler is that we're going to introduce a new set of quarks to form mass terms like this. So we're going to have some like SU2 left charged prime quark that can form a gauge invariant mass term with Q tilde. And then some SU2 left singlet down prime, which can form a gauge invariant mass term with D tilde, and the same for U and U tilde. So we can't do that now with the current gauge assignments, but that's what we're going to end up with. But we have to play some games to do this. All right, so we introduce the prime sector. So before we had SU6 breaks to SU3 color and SU3 tilde. And so now we introduce a new gauge group that isn't living inside the unified color group, so this SU3 prime. And now SU3 6 cross SU3 prime, I'm going to like conceptualize this breaking as 2 breakings, but really it's just 1. So first you break SU6, so you get SU3 color, SU3 tilde, and SU3 prime. So this guy's just being left alone under this breaking. And then we break these 3 SU3s down to 2. So SU3 color is now left alone. And we take the tilde in the prime sector and we break it down to SU3 diagonal. And so what do we gain? So we introduce, above the cut breaking scale, we have SU6 and SU3 prime. And so we have these 6 split fields that have living inside them the tildes that we don't want. And now we've introduced this new prime matter content like this, which sort of mirror the 6 splits, except they're charged under prime. And then we still have the massless quark, and we've introduced this scalar delta that's responsible for this full color unification breaking. And so with these prime fields, these primes can now pair up with the tilde fields to form mass terms, right? So we can form terms like, well, Yukawa terms above the cut breaking scale, like Q prime delta Q, right? Our Yukawa terms that give mass to the primes look like this. And then we have our delta field, which attains a VEV at a minimum that looks like this. And so it's like has 0 VEV in sort of the QCD side of this matrix, and then identity in the tilde side. And this VEV pattern grabs only the tilde quarks out of the spectrum, which is what we want. And so then below the cut breaking, we have mass terms that look like these kappa Yukawa terms put together with the VEV form a mass. And then we have these Q prime, Q tildes, U prime, U tildes, D prime, D tildes. And they're all gauge invariant. So this accomplishes the task of forming mass terms for the Q tilde, U tilde, and D tilde fields. And so note that in this scheme, above and below cut breaking, SU2 left remains unbroken, which is essentially essential, so that's good. And for now, we take all the kappas to be order 1. It's possible that the kappas could be hierarchical, like the standard model Yukawa couplings, and I can talk about the implications of that a bit later. But for now, let's assume the kappas are order 1, so the masses of these tilde quarks are going to be around the cut breaking scale. And so now we have exactly what we want. These tildes are much, much more massive than Q because they're sitting up at this color unification scale. And the strong CP problem is solved, almost. Does anyone know why, almost? Yeah, I've introduced a new non-abelian gauge group with its own theta CP. So just to summarize, this is the theory so far, above and below, before we deal with the SU3 prime. So we have the normal standard model field content here. The blue is our prime sector, and the orange is our massless quarks. And this is the scalar field responsible for cut breaking. And then below, it looks very complicated, but everything below this line is very massive and sitting around the cut scale. So at the cut scale, we have the tilde quarks and the prime quarks, and they can form nice gauge invariant singlets because they're all charged under SU3 diagonal. Our massless quarks are still living below the cut breaking scale, and then the normal standard model stuff. So we finally have the low energy effective field content that we wanted, so that's very good. And so now we have to deal with the theta prime issue, right? So we've introduced theta prime. It has its own instantons, and so we get this own theta prime and theta 6. And then when we break down to diagonal, this theta 6 and the theta prime contribute to the G diagonal GG dual. And then we have theta 6 only contributing to QCD. But in general, through the delta, these guys can mix, and this can contaminate the QCD CP violation. So theta prime has to be removed. This requires even more model building, but I will take this moment to remind you that all of this still is really stemming from the problem of decoupling the partner fields in unification. So still, all this model building is just trying to decouple these tilde partners. In order to do this, we propose two UV completions. So the first is to add a second massless quark charged only under SU3 prime. So this looks a lot like Choi and Kim. And we like this model better, so we're going to spend more time on it. The only downside of this model is that it requires higher cut scales because this massless quark is charged under SU3 prime and will eventually be charged under SU3 diagonal, and so it contributes to the running between the cut scale and the confinement, the diagonal confinement scale. So this slows down the running a little bit. So to get confinement scales we want, we have to raise the cut scale. So that's the only downside. The nice thing is that both axions are dynamical with the scale set by SU3 diagonal confinement. And then in the second UV completion, we introduced a second delta, really just like the old PQ mechanism. So we endow our Lagrangian with a U1 Pechi-Quinn symmetry, and then we get a resulting axion which absorbs theta prime. And this is sort of a hybrid dynamical axion, normal axion solution. So let's talk about model 1 first.
So that went kind of fast. Sorry, I mean so there is a standard axion, and it does couple the way a standard axion does. Or are you going to talk about that? Or?
Yeah, we'll talk about model 2 as well as model 1.
Okay.
Yes. So like this in model 2, we're not. It's sort of like we'll do model 1 first, and then model 2 is sort of like has some differences, so we'll go over it in some sense. But yeah, there will be another axion in this that absorbs theta prime axion if you want. But remember, these are like two issues that are solving this like theta SU3 prime, which is sitting very high. So these are kind of like UV completions, but they do have like pretty important implications for the phenomenology. So, all right, so let's talk about model 1 first. So model 1, we introduce a new massless quark, the chi. It's charged as fundamental under SU3 prime, and so under the cut breaking, it ends up as fundamental under SU3 diagonal. And then we still have this psi, which was charged under the 20 representation of SU6, and then gets charged under a box bar for color and SU3 color and SU3 diagonal. And remember our goal, we really want SU3 diagonal to confine at a higher scale than QCD. That's pretty important for our model, right? So we have all the matter content for both theories now, or for the theory, and we have our boundary conditions. So if SU3 diagonal is formed from QCD and SU3 prime, then we get this boundary condition. So at the cut breaking scale, 1 over the gauge coupling of the SU3 diagonal group is the sum of 1 over QCD's gauge coupling and 1 over SU3 primes gauge coupling. And then also at the color unification, QCD is equal to the SU6 gauge coupling. So with these boundary conditions and with our field content, we can calculate the renormalization group running. So here's an example of an RG running. So we have the RG scale in GED on the x-axis, the value of the couplings on the y-axis. And so the black line here is the SU6, the color unified group. The green line is SU3 prime. So SU3 prime and SU6 break together to form SU3 diagonal, which is the blue line. So you can see it's slightly smaller than SU6. And this runs, and because at this point here, we assumed all the kappas are order 1, and so this guy runs faster than QCD. QCD is shown in red. And you can see that you get the diagonal to confine at a high scale. And we calculated both the 1 loop running and the 2 loop running. The 1 loop is the dotted and the 2 loop is solid. So the 2 loop gives us a slight improvement on high scale confinement for SU3 diagonal. And we have QCD in red. And for this confinement scale is 4 TeV. So we were able to accomplish, and then our cut breaking scale, we were forced to push up to somewhere between 10 to the 14th and 10 to the 15th GeV. So we're able to accomplish this, this unification story with the boundary conditions and a high confinement scale for SU3 diagonal, given both the psi and the chi matter content, which is good. And then earlier I said I would comment on the kappas. So if the kappas are hierarchical, right, what that means is that not all the tildes get integrated out here, right? Some of them are sitting at various scales, and it affects how quickly this confines. And so if they're all spread by like 10 to the 6th, like from 1 to 10 to the minus 6, like the standard model Euclid couplings, we couldn't get high scale confinement, but we were able to accommodate by pushing this color unification scale up near the Planck scale. We were able to accommodate like 10 to the 4 spread in hierarchical Euclid couplings. So this does work for some tuning in Euclid couplings, but not, we can't just mimic the standard model tuning for this model. All right, so what happens when SU3 diagonal confines? So again, there's this U4 symmetry that's broken by psi bar psi, chi bar chi, psi bar chi condensates. So you get U4 left cross U4 right, breaks down to U4V. You get 16 pseudo-Goldstone bosons. So you get some that are adjoint under QCD, fundamental under QCD, and singlets under QCD. So these are sort of like the eta and the eta prime. And so there are exotic pion masses actually obtain pretty high masses, right? Because the pions are charged, at least these guys, so these pions here, are charged under QCD, right? So they interact with gluons. And these are kind of, at least to me, very familiar Feynman diagrams because they're like the quadratically divergent contribution to the Higgs from interactions with gauge bosons. So these are quadratically divergent. So these diagrams push the mass of the colored pions up to the cutoff scale of the theory, which is the confinement scale with the diagonal. So, and then it's that times the strength of the interaction times quadratic Casimirs. So the adjoint and the triplet are both pushed up to the cutoff scale of the theory, and then they have different group theory factors in front of them. So you can calculate the mass of the pions that way. And then the singlets, you can calculate their mass through their anomalies. So the etas have associated currents, so you can write down the divergence of these associated currents, where we're going to introduce the scale FD, where FD is related to the confinement scale with the 4 pi. And then you can see that these chi's coupled to this G prime dual, and the psi's coupled to G6 dual. And from the divergence of these currents, you can write down a potential for the etas. So above the cut breaking scale, we get this effective interaction for the etas, where the eta psi prime talks to SU6 GG dual, and the eta chi talks to the SU3 prime GG dual. And their dynamical scale is the scale associated with the confinement of SU3 diagonal. And then below the cut breaking scale, we get this interaction of the etas with the GG duals, where one talks to QCD and one talks to SU3 or SU3 diagonal. And so note that the Axion scale here is FD and not lambda cut, which is kind of nice, right? Because a lot of our undesirable physics is suppressed by lambda cut, right? But our dynamical axion scale is FD, and these are naturally very, very separated by the RG running. And then if you include the QCD eta prime, you can write down all the pseudoscalars that couple to GG dual, and you can get an effective potential for all of them, right? And you'll see that at this point we're a little bit depressed because we've just recreated an invisible axion model, right? We have, which maybe you guys saw a few slides ago, you were maybe predicting this, right? We have 2 masses for 3 pseudoscalars. So we haven't like really provided a source of mass for both of our dynamical axions to get massless, or to get massive. So this is sort of exactly the same story that Joy and Kim had, right? But we found an alternative source of mass for our axions. So typically, everybody ignores this when they talk about axions, because at high scale, QCD's gauge coupling is very small, right? It's asymptotically free. So normally we can ignore non-perturbative effects from QCD, right? But if new physics alters the renormalization group flow, large couplings can induce new instanton corrections to the axion mass, right? So this has not been discovered by us. A long time ago, this was predicted by Diamond Seiberg and Pullman and Peskin. And then Flynn and Randall actually computed these instanton effects and how they affected axion mass. So Flynn and Randall assumed that at some high scale M, there's a lot of new matter content charge under QCD. So much that not only does it slow down the RG flow, but it actually reverses the sign. And so QCD starts to increase up into some scale at breaking, which they assumed maybe this guy's living inside a gut or something. And so from here on, QCD maybe goes really small, and they neglected the instanton effects. And they calculated instanton effects in various scenarios here. Very recently, Agrawal and Howe wrote a paper factoring the strong CP problem, where they said that QCD is living inside some SU3 cross SU3 cross dot 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 cross SU3, and all of these break to form QCD, right? So you think at first, like, how could this possibly help a strong CP problem? They introduced a million new strong CP problems, but what they got from this was that they have exactly the same breaking pattern, right? At the breaking scale, the gauge coupling for QCD is related to 1 over the first exotic gauge coupling plus 1 over the second exotic gauge coupling all the way up. And so one of these could be huge, right? And it would have a very, very small contribution to the phenomenology of QCD, right? Or to the gauge value, the gauge coupling value at that scale. And so they were able to sort of pump up the QCD values. And so in both of these scenarios, we have a non-abelian gauge group at some high scale with a very large gauge coupling. And in that case, then instantons start to have a non-trivial effect on the axion potential, or any potential of the pseudoscalars. So if they're going to have an effect, we should calculate it. And then, sorry, one more thing I should say is this case is the one that applies to us, right? Because if you go back to our RG flow, this guy is very large, right? So this guy is going to be the guy that's our source of axion mass from instantons to the SU3 prime. All right. So the first step is to just sort of estimate, like, do instantons have an effect for our model, right? So at the first order approximation, you can just do the dilute instanton gas approximation, assuming there's no fermions in your model. And you get this d rho over rho to the fifth times the instanton density. And the instanton density is this typical, like, exponential suppression for small values of the gauge coupling times these prefactors. And lambda SSI will be like the non-perturbative contribution to the potential for instantons. So before we had all these lambdas that were the scale of the GG duals, we're going to have an additional source of mass through lambda SSI. And for our benchmark, which is the one I showed you for the RG flow, alpha prime at the cut breaking scale was 0.3. And in this first order approximation, for this benchmark, you just do this calculation. You get that lambda SSI raised to the fourth is like 10 to the minus fifth times lambda cut raised to the fourth. So if you take the fourth root of all this, it's sort of like this lambda SSI is like 1 or 2 orders of magnitude less than lambda cut. So you remember our lambda cut was huge, right? Our lambda cut sitting here. So in this first order approximation, these instantons are having effects like 10 to the 13th or something. So these are like huge effects. So maybe we should do this more carefully. But it seems like at least it's promising that instantons in our model do have a large effect on the axion mass.
Sorry, can I ask
Yeah.
a question? So I don't understand, I don't remember the hidden axion model well. So first my question is, is this correct? Is this a correct way of thinking about those models, that I have some sector that has in some limit has an exact U1
Yeah.
and makes a Goldstone boson. But then if I include QCD, that thing would be an axion, and we get a tiny QCD mass, right?
Yes.
So far it just looks like something sitting on top of a normal axion.
Yeah.
But then the additional thing that I do, that in that high scale, I also have the option of breaking that U1 explicitly by a tiny amount. And then when I do, I get an additional source of mass for the axion.
Yeah.
So that gives me the additional parameter, and if it's small enough, it'll still work and be the axion, right?
Yes.
That's it.
Yes.
So if that's correct, then I want to understand, in your model, you have more moving parts, but before you got to these instanton corrections, you had a similar setup, right? I mean, the problem is that you have, in your high sector, ignoring ordinary QCD, you would have an exact U1, so you would just get an ordinary axion, I think. And, well, I guess what I'm asking is that it seems to me that in order to get an additional contribution to the axion mass, whatever the new thing you're looking at should break some additional symmetries. I guess that's what I'm not understanding. Like in the invisible axion story, right? You have to break some additional symmetries at the high scale, otherwise you wouldn't get anything. But the way instantons, I don't see them as breaking additional symmetries.
So, yeah, I see what you're saying, because like mostly the pseudoscalars couple to anomalies, right? So like you can think of these like anomalous contributions to the masses as being like you break these symmetries and you get these extra contributions. So I don't really know, I mean from a zoomed out point of view, I don't really know how to answer your question, except to say that like these GG dual stuff is like, at least like from my point of view, kind of complicated interactions with the QCD vacuum, right? So naively, like in most models, this contribution is just very small to the potential.
Oh, I think, wait.
And here it's very large. I don't know, like.
Is this what it is? So just going back to I just want to see why, just trying to understand why there should be some, perhaps large correction to the axion mass. Is this the story? So if I had the invisible axion set up, and I didn't, so I just had the ordinary axion before I included some explicit breaking.
Yeah.
But now I don't do that, but I have a model where at some high scale, alpha QCD was big because of this running effect at the high scale. And then the statement is that the QCD contribution to the axion mass, which is always there, is now much bigger.
Well, it's the SU3 prime, but yeah, that's exactly what's going on, is that this SU3 prime is
mixing all these
altering the
gauge
potential
groups.
of the axion, and
So
giving it this large mass.
I see. I can think of it that way. So I
Yeah,
can think of these as being the QCD effects, but they're bigger because at the high scale the alpha is bigger.
Yeah. So to be more technical, it's not QCD though. It's this exotic SU3 prime.
Okay.
But it's true that like whatever our low mass pseudoscalar was some combination of the things that are coupling to G prime and G6 or G diagonal and G QCD. And like we didn't have enough sources of mass for all the pseudoscalars that are coupling to GG dual in our theory, right? And I think it's because this extra whatever these effects were highly underestimated, because at high scale SU3 has large instanton induced effects on the axion potential.
Okay.
Does that answer your question? I think you kind of answered your own question. I confirm.
Okay, good.
Is it clear why these new instanton effects just affect the axion and not the regular eta?
So they affect all the pseudoscalars, right? So you get some pseudoscalar mass matrix and you diagonalize it. And at the end of the day, I'll get to that eventually, but at the end of the day, you'll see that assuming all these scales are separated, you could sort of approximate that one pseudoscalar goes like the biggest scale, which will be, in this model, lambda SSI, the small size instanton scale. Another one will go like lambda diagonal, and then the last one will go like lambda QC, which will be, and will reproduce the standard eta, meson, and stuff. So, yeah, I mean, if this scale gets too low, or the SSI instanton scale gets too low, we will mess up the the meson mass spectrum, but that's kind of like, that's not too confusing, right? That makes exact sense. Like, we want to keep the new physics at high scale so it doesn't mess up our normal QC story. So. All right. All right. So this is a very naive estimation. Showed that these instantons had a huge effect, right? So we can't just ignore them, is what this tells us. So we have to actually do the calculation. And we don't have a theory without fermions, right? We have quarks charged under SU3 prime, so they're talking to our instantons, right? And so you can actually calculate this suppression in the presence of instantons in the presence of fermions. So Schiffman has a really good paper on this from a long time ago, and then Flynn and Randall do this really explicitly for a few models that you might find interesting. So for our model, it's the SU3 prime instantons, remember, that are non-negligible. So the way you insert an instanton into a Feynman diagram is you put all the fermion zero modes in, and then assuming you're trying to calculate a contribution to a potential, you want to close off all the loops so there's nothing left. If you were calculating like a bare mass, maybe you do something else. All right, so what we do is we have our prime quarks talking to the instantons. Our prime quarks have prime Euclid couplings that talk to the standard model Higgs, although at this scale the Higgs is active, so we get loops. And then we also have these chi's, which are massless and get closed off by their condensates. So we get the normal. So if you calculate the instanton contribution to potential, you get the normal dilute instanton gas density stuff times a suppression factor, which varies depending on whether it's mass or condensate or a Euclid talking to an active scalar. And then this is the leading order effect, which is just the prime sector. I will comment quickly that there's a sub-leading effect, which doesn't affect this model, but will become important for Model 2. Yes, and I think I have time to talk about Model 2? Yeah.
Sorry, so I wanted to try to understand.
Yes.
So if I had some perhaps very complicated model like yours, and but I don't know if your model, I can't tell whether your model has this property or not, but in my complicated model, maybe it's your complicated model, all the gauge groups are not asymptotically free.
Yeah.
Okay, so they're getting strong in the UV. And then I'm looking at some kind of instanton contribution in those kinds of models.
Yes.
So in an asymptotic, in a theory like QCD, which is strongly coupled in the infrared, the sum over instanton is dominated by large instantons, and it's out of control because of the IR stuff. Here, it's the opposite. It's out of control because of the UV. So
Not in my model, but in this model,
but
yes.
in my model. So I'm asking a conceptual question. It's not.
Yeah.
I'm just trying to.
Yeah.
So in such a model, what would presumably be the case is that at some point I have to cut off the theory. The theory has to be UV completed into some theory that isn't getting strong in the UV. So okay, so I do that now. But now it seems like I have just some UV-dominated contribution to the axion mass, and I can kind of get whatever I want.
Yeah.
Is that true?
So
Is
I think
thinking about this right?
there's a regime in which this is not calculable, right?
Well, it
so
depends on the UV.
it depends on the value. No, it depends on the value of the gauge coupling at any point at which you're trying to calculate something. You want to be able to use the dilute instanton gas approximation.
I'd have
So
to cut
you
it
need
off
a
soon
gauge.
enough.
Yeah, you need a gauge coupling that's living around here. Maybe you can get away with a little higher, but at some point, this guy gets too large and the dilute instanton gas approximation breaks down. And then you have non-perturbative
That's when
physics that I don't
I have
understand.
to cut it off before it gets
Yeah,
started.
so in all the papers I did, factoring the strong CP problem is like mine. It gets away with it because it is, from this point of view, this high energy theory has an IR boundary, and the large instantons effects are coming from the IR of this theory, right? But it is non-perturbative, so it's affecting the low scale
I mean,
physics.
it seems like this, if this is true, this could even happen. I mean, if you write a gut, an ordinary gut, one of the biggest problems you have in writing down a gut theory is that it's totally non-asymptotically free above the gut scale, because you have all these big representations to get double triplets.
Yeah,
and all this
so,
crap. So in a theory like that, if you looked at gut instanton corrections to the one and only theta parameter in that, it seems like you could get very large contributions that have to do with the
to
details
pseudoscalar
of the
masses,
gut.
Yeah, I don't know.
Okay.
That's a good question. I mean, I would say that if you have a non-abelian group that has a Landau pole, I don't know what the physics looks like. All the stuff we've calculated are assuming that it stays in the dilute in some gas approximation over some regime, and then at some point in Lisa Randall's it breaks and goes to a gut that just has exponential suppression, or like very, very quick drop off of pH coupling, and then in factoring, we still have asymptotic freedom. We just set it at a higher scale. So yeah, that's a good question. I have no idea what happens if it actually hits like a pole.
No, we're not going to hit the pole. We'll stop it before it hits the pole. But then the point is it depends on where you stop, and so
Yeah.
it's completely dependent on the UV completion, and so it could be anything.
Yeah.
And if that's the case, then it seems to me that the axion mass could be anything. If that model actually worked, it would be the world's simplest model for an axion mass, where the axion mass would be anything.
Yeah. So
So
maybe
it'd be worth understanding.
maybe it's
whether
worth
that's true or
understanding
not.
why people haven't done more of this. If there's like
know.
some reason this isn't contaminating low energy physics. But like, yeah, this is a game people are starting to play. So I don't know.
Okay.
That's a good question. We're not the first one to use instanton effects to contribute to axion potential. So I don't know. That's a good question. We should think about it. Maybe we can write down the world's most simple axion paper.
Yeah.
Yeah. All right. So there's also a subleading contribution, which isn't relevant to Model 1, but will be relevant to Model 2. So in this subleading compression, we have the SU3 prime instantons, and we have the prime quarks here, and then they interact with a delta that flips a prime quark to an SU6 multiplet. And then the standard model Yukawa couplings to the Higgs are the guys that close off these fermion loops. So this is a far more suppressed diagram, but it will be relevant in Model 2. But for Model 1, this is the leading order suppression. So this guy is the one we care about. All right. So with the fermion suppression, we get a much larger suppression on the instanton contribution to the potential. So with the same benchmark, alpha prime equals 0.3, we get that this lambda SSI to the fourth goes like 10 to the minus 11th times lambda diagonal contributions and 1 lambda cut. And so we get that lambda SSI is sitting at a few TeV. So the instanton effects generate a new contribution to the effective potential that affects the mass of the eta chi, because chi is the guy charged under SU3 prime. And so the full axion potential, we have this potential that affects eta prime pi and theta prime bar, and from lambda SSI. We have the lambda diagonal confinement contribution, and then we have QCD, which is talking to eta prime psi and then theta 6. So we can write down this pseudoscalar mass matrix and diagonalize it to get mass eigenstates, right? So we write down the whole mass matrix. We get contributions that are like the instanton contribution sitting here, only talking to one corner. And then the confinement guys talk here and here, and then QCD talks here. And remember, lambda SSI is a few TeV, you can get as high as 10 to the fourth, and lambda diagonal we require to be a few TeV. And so we can plot our dynamical axion mass eigenstates. So there's two sets of colorful lines which correspond to two different eigenstates, some mixture of eta prime pi and eta psi, so it doesn't really matter which is which. One should be more faded than the other. But within one set of colorful lines, I can tell you what's going on. So on the x-axis, we have the value of the alpha prime coupling at lambda cut. And on the y-axis, we have the mass of the dynamical axions. And then for some sets, for some curve that goes like this, the purple line is lambda cut sitting near the Planck scale, 10 to the 18th GeV, 10 to the 17th is the red, 10 to the 16th is the green, 15th is yellow, and 14th is blue. So you can see that if we vary lambda cut, we get different contributions to the axion mass. The other really important thing to see is that this guy is highly sensitive to the value of alpha prime at lambda cut, which is exactly what we'd expect, right? For low values of alpha prime, the instanton contribution turns off and we just get some light axion, right? So that's good. And then you'll also notice that these solid lines turn into dotted lines at some point. And this is the point at which, so at this point, for this value of alpha prime and this value of lambda cut, here we get that the confinement scale is below 3 TeV. So below here, we start to get dangerous phenomenology in terms of low scale bound states, right? And that makes sense that, you know, these low lambda cuts are going to have more parameter space ruled out, higher lambda cuts have less parameter space ruled out via this mechanism. And it also makes sense that both eigenstates see this happen at the same time, because lambda diagonal is a function of alpha prime and the cut breaking scale value. All right, so physically, what do we get from this? Well, we can see that we've been way too good at making our axions massive, right? So for everything except these Planck scale cut breakings, we basically get that we have masses that are 10 TeV for our axions, right? For both axion mass eigenstates. So they're out of collider reach, right? Aside from a little tiny corner of parameter space that's maybe not too believable. So we've been very, very efficient at pushing up our axion masses, perhaps too efficient. And then, yeah, this is basically, these are the two largest mass states for the axions. And then, one other thing I want to say about this. So another comment on the kappas. So remember when I said before, all the kappas are order 1? If the kappas aren't hierarchical, but they're all order 10 to the minus 1, that's exactly the same as pushing the cut scale down a value, right? So if we had a cut scale of 10 to the 16th, but all our kappas were 10 to the minus 1, we'd have a line that looks a lot like the yellow line, right? And if we had 10 to the minus 2 and a lambda cut at 10 to the 16th, we'd have a line that looks a lot like the blue line. That's if they're not hierarchical, but they're all less than 1. So you can sort of get a sense for our sensitivity to the kappas looking at this graph.
So if I look at a conventional hidden axion model, so I have this additional thing, this additional tunable parameter, which is this breaking of some what would otherwise be an exact U1 PQ type symmetry in my UV theory. Now I can choose that to be whatever I want, right? So nothing stops me from making the axion, 10 GeV, 100 GeV, TeV, as big as I want. But my sense is that you can't keep solving the strong CP problem forever,
that's
right?
true. That's what I'm
that would be
arguing.
way too good to be true. And so you can see how that would happen, because the bigger, so if you for example, one of these dynamical axion models, the more I break that symmetry, the more that breaking is just going to induce
the farther away you get from
the mass that gave me allowed me to absorb the theta, blah, blah, blah. So you can see that it can't work forever. And it just seems, even though I can't see all the steps in my head, it seems like the natural guess is that it stops working exactly when the axion mass starts going above 1 GeV. And that just seems like, so that's my guess as to what happens in a simple model like that. And it's also my guess that that's true even in a complicated model like yours, where I'm even less able to track through all those things, right?
Yeah, so
you see what I'm saying?
an explicit U1...
Does it really make sense to talk about axion masses above a GeV?
Yeah, so an explicit U1 breaking model, right, would mean that the axion is going to be displaced a bit from the CP-conserving minimum. Its minimum is going to be somewhere else, right? Would you agree with me there?
Yeah, I think so.
Yeah, so here the CP-conserving minimums are this guy and this guy can have the same CP-conserving minimum. We're just pumping up this, right? So I'm pretty sure, at least from a high energy point of view, this CP violation is
Well, I can't follow the details, but you
Yeah.
can see why I'm saying this sounds too good to be true. It sounds, because then you get to integrate, why stop at 1 TeV? Why not go up to the biggest, 10 TeV, 100 TeV? As high as your model will let you go, and you just integrate out things there, and amazingly you have theta equals 0, no strong CP problem, but no light states. That just sounds like that can't be right.
Yeah, so, I can tell you where our model breaks, but maybe this won't be answering your question. We can't push our cut breaking scale past the Planck scale, and so we can't put lambda diagonal too high.
That doesn't, that wouldn't,
Yeah.
that's... Anyway, I don't know if we can answer this now.
So
but
maybe
I'm
we
just
can answer
telling
it.
you,
I know at least our high
I think
energy
it's something
effective
to
theory
think about.
has a CP conserving minimum.
'Cause, at least...
And the instantons effects don't tilt the potential away.
I do know very well the Schiffman-Weinstein et al. paper.
Yeah.
That one I studied when I was a little kid. But the whole point of that paper is that you can understand the axion mechanism both from a UV and an IR meaning below the QCD.
Yeah.
You know, the fact that those things agree was the whole point of that paper.
Yeah.
And that just means that obviously cannot, that has to break down if you say the axion is heavier than a UV. Because then it's just a miracle that theta is 0 in the low energy theory. It is not, you see what I
Yeah,
mean?
so, yeah, I think we can talk about it. I'm not sure this is such a problem though. Like, it's true that like theta prime, the guy that's absorbing theta prime is really massive, but theta prime isn't even active. Theta prime is a UV, not a Billion gauge group, right? So like this theta problem is like a thing that only very smallly contaminates low energy physics, and it kind of makes sense, at least like in this very zoomed out point of view, that its axion is very heavy, right? And it's corresponding to like where the scale matters, right? Which is near the cut scale. And then this guy is like really is like most of its mass eigenstate is associated with theta 6, right? Which is the one that talks very directly to QCD. And this guy isn't sitting like too high, except that it's like a collider observable axion, which we are not the first people to write down collider observable axions that are like sitting at 750 GeV, for example. There's a lot of papers like that. So.
Well, I'm just saying,
So
it
maybe
wouldn't
we can
solve
talk
it.
about
I'm not
after.
saying it couldn't be there, I'm just saying I don't think it would solve the strong CP problem. But I don't think we're going to resolve this now.
Yeah,
I
I
just wanted
mean,
to make that comment. It's
yeah,
maybe
definitely.
Maybe something to think about.
I don't think these 750 GeV papers were saying it's an axion-like particle. I think they were saying that it's solving the strong CP problem. But we can talk about it after. It is something to think about. The other thing to think about that maybe also fits in your description is that these ADAs are having masses above the confinement scale, right? So like really we should be talking about masses of bare quarks, which we're working on now. So that's another thing. Like these ADAs aren't really bound states above this scale, which maybe is also getting to your like suspicion of where the EFT breaks down. But anyway, but what is the low? I'm almost done, so don't worry, I won't hold you too long. So the low energy spectrum is that we have the eta prime of
slowed you
QCD.
down, so don't apologize.
It's okay. It's actually good to be slowed down. So we have the eta prime of QCD plus the rest of the standard model spectrum below lambda diagonal. In most of the parameter space, the axions are too heavy to produce at colliders, but we do have exotic QCD colored pions. So we have these color octets and color triplets. And then we also have these sterile neutrinos suppressed. All their interactions are suppressed by lambda cut, and they're basically invisible because they're singlets under all the standard model gauge groups. And the collider pheno, so I skipped over model 2, but if you're interested, we can talk later. So the collider pheno is that, only for now, we'll talk about the pions. These pions can be produced at colliders. They're charged for QCD, so they can be pair-produced through their kinetic term. And then they also have this anomalous way to talk to gluons, so they can be anomaly produced, singly produced via the triangle anomaly diagram. And actually, there are limits on adjoint QCD colored scalars. So there's gluon searches where the color,
It's color on it, right? It's color on things.
Maybe,
So
yeah.
indicated 2 jets each, and you have these 4 jet multi-resonance.
Yeah, maybe we could talk about this because we're really interested in the triplets right now, is what we're working on. But yeah, the adjoint guys, we have these gluon searches. They're produced through the kinetic term too, so they have really the similar calculation for the cross section. So their cross section is shown in purple here, and so they're ruled out up to about 700 GeV. And so if the mass of our octet pions are 700 GeV, then that puts a bound on lambda diagonal to be about 3 TeV, which you can tell I was anticipating based on the 3 TeV being where all my benchmarks were. So in conclusion, the strong CP problem can be solved using massless quarks and unification. And so we have this unification that's SU6 cross SU3 prime, breaks to SU3 QCD and SU3 diagonal. We can arrange the confinement of lambda diagonal to be larger than QCD by decoupling the standard model quarks. And decoupling the SU6 partner fields requires significant additional model building above the cut scale. We implemented this in 2 ways. Model 1 had 2 massless quarks, and Model 2 I didn't get to talk about, but it's a massless quark and an axion. And then in conclusion, small size instantons provide an extra source for the massive axions. And then a generic feature of both models is that there are 3 sources of mass for the 3 pseudoscalars, so we're able to push all the axion masses up. And then the two scales, lambda cut and lambda diag, are naturally separated by the RG flow of the couplings. So that's kind of nice, because we get some pheno advantages here and some, lack of tuning advantages here. And then the most promising collider signals so far come from exotic pion color octet searches, and we're still working on the triplet pheno. So thank you very much. Yes.
Is the eta prime QCD weakly interactive with standard model of matter? And can it serve as a dark matter candidate?
I don't think the eta prime can be dark matter. It's
Because if one of those heavy axions can weakly interact, then you can constrain the parameter from web searches.
yeah. So our eta primes, some of them might be dark matter candidates. I don't think the standard model eta prime can be. But yeah, there is axion. I mean, so ours couple like normal axion, so they couple to photons. But I think there is some like axion-like dark matter that somehow plays games, either suppresses the coupling to photons. I don't really know the whole story about axion dark matter. But I know axions are dark matter.
All I'm just suggesting is that some of those heavy WIMPs can be constrained from the recent WIMP searches that are available, so you might get some constraints on your parameters.
I don't think so.
I mean, I think generally, the eta prime is generally not stable, but however, if you look at some of these heavy eta primes, like in the hidden axion things, again, you have to break some symmetry, you have to break it by a small amount. I mean, it's a good guess that maybe those things, some of those could be stable in the limit where you turn off that breaking. So if that breaking is small enough for a very high scale, this sort of hidden sector, there may be something stable in that hidden sector. But probably a heavier thing, I would guess. But that might be something that worth looking at.
When they all decay to 2 photons, then it's one need to check whether they become in the ideal universe.
Yeah, I'm not thinking that it would be the eta prime itself. But the point is that there is some chiral symmetry that you are breaking explicitly, and so there may be some discrete symmetry that some other things are charged under that might be stable, like some hadron in some one of these sectors.
That is a thing. So we actually have some undesirable cosmology in our models. So we invoke maybe we have low scale inflation, everything we don't want inflates away, and we leave the exercise of using our undesirable cosmological relics as like tuning them so that they're desirable and creating dark matter. But that's kind of a future exercise. But yeah, there's this question of domain walls associated with the color unification breaking, which are fine if the inflation scale is lower than the unification scale, stuff like this. So yeah.
Yes, you have color triplet PNGBs.
Yes,
Aren't those stable?
they are. That's what we think
So
right now is that
there
they're
are
stable.
hadrons, right?
Yeah,
There
so
are hadrons.
they were looking at stable because they have nothing. We can't write down a Feynman diagram such that they may. Yeah, so we were thinking they're stable. This is sort of the last step. We're thinking they're stable, and we're looking for these colored stable states. So yeah. So yeah, maybe actually our initial analysis is that those are stronger bounds than the pion, but we haven't finished it, so I don't want to show it.
Okay, let's thank Rachel again.